What are phasors? So I will be starting the topic phasors. For that we need to just learn the beginning of complex number. This is the argon plane, this is the imaginary plane, this is the real axis plane, and consider a vector r z, take it z. When it is rotated by an angle theta, we can represent z dash, length is z, as z dash equals z e to the power I theta, and we know z e to the power I theta is cos theta plus I sin theta. For your information, cos theta plus I sin theta to the power n equals to cos n theta plus I sin n theta. This is known as the De Morgan's theorem. You can prove like this. This you take e to the power I theta, e to the power ni theta will be cos n theta plus this is DMT, De Morgan's theorem. I just told you the basics. Okay. Yeah. So the key insight is when we are multiplying this with e to the power I pi by 2, it is rotating the vector by 90 degree. Okay. It is simply e to the power I cos pi by 2 is 0 and I pi by 2 is I, so it will be e to the power simply I, or we can write it simply as I, right? So it creates a transverse vector, right? And I'm giving you one trick. You can take it as a derivative trick. I have learned it from SM Professor, sir. You can watch his videos too. So what is the derivative trick? We can just convert calculus to algebra. We can apply the algebraic sense in calculus. So dz by dt, take z as z naught, or z dash, take it dz dash e to the power I theta, right? uh, yeah, or you can take it as a e to the power I omega t. Dz dash by dt is you can see a omega will come outside and it's I e to the power I omega t. So we can write it as I omega z. Why I came here? Because we are derivating with respect to time period. When we are taking derivative, so I omega will come outside, right? It's I omega z. So d squared z, you can say also d squared z. Now the double derivative is I omega whole square z. So it's minus omega squared z, right? It's the derivative trick. So what are phasors actually? So phasors are just complex functions, like x of t is real part of z of t plus we can take it as the phasors. In physics, when we are talking about phasors, we only take concern about the real part. The imaginary part is required for calculating impedance, but in calculating the overall values, we take only the real part. It's real. Okay. So for AC circuits or the RLC resonance, resistor RLC resonance, resistor, inductor, and a capacitor resistance, the equation looks like L d square I by dt square plus R di by dt plus I by C dv by dt. Right. We can just do nothing, but we can compare this to the equation of the damped oscillation. It looks like this: bx plus or b dx by dt plus kx equals to L di square by dt is dv by dt v naught v. Yes, kx equals to f naught, right? It's the equation of a damped oscillation. In the RLC resonance, the same damping is done by inductor. Here mass is replaced by inductor, the damping constant is replaced by resistance, and C is capacity. 1 by C is replaced by K. K is replaced by 1 by C. So this is the importance, and we will talk about impedance. So I will talk about impedance. It's very easy. I will give you two actually. This is the first method. I will give you another method for doing the complex number, which is given in NCRT. This is only for, I think, INPHO or NSCP. Okay. So impedance. What is impedance? Impedance is a complex resistance in an AC circuits. It is given as Z equals R plus I omega L minus omega C. This is the imaginary part. We are not concerned with it, but we are concerned with the resistance. So the VR equals IR, we all know. VL equals LDI by dt. VC equals 1 by C integration I dt. We all know this, right? So assuming I of t as I naught e to the power I omega t, we are using the trick di by dt, the derivative trick is here it's then I of t into I into omega, right? We can write it like this, and integration dt can be written by 1 by I omega. As simple as that. It's very easy. I dt. So here we will do integration I dt. It's I by LC. So just put this in the equation of the equation we know. What we know, the equation is V equals VR plus VL plus VC. It's I R plus I di by dt. Di by dt is I omega. L. It's I plus what we know, I by integration IC dt. So 1 by I by omega c. We have got it here. I by I omega c. So from here we can clearly get the equation which we have got further earlier, that V equals I into R plus I omega L minus omega C. Now keep a thing in mind. This is the complex this is the voltage source of the AC circuit, which is V naught sine omega t, you can take, and this is the current, which is the RMS current, and this is the complex resistance. It's totally called the complex resistance, or you can say it's the impedance. Okay, so nothing about that. And if we talk about this, if we got Z equals R square, Z I am taking as the complex impedances value. It should be omega L minus, you know one thing, right? The Z, if it's Z A plus IB, then the mod of Z is root under A square plus B square, which is the amp or amplitude. You know that it is the same logic. Here it's R square plus omega square. So to maximize Z, we have to minimize this. So it will be minimized when it will be 0. So this term will be 0. 1 by omega c is 0. So what we will get, omega equals 1 by root LC. This is the condition for resonance in LC circuit, in RLC circuit, right, or dam circuits. This is very important. You can keep this in mind. And talking about another thing, I am just giving you another approach for solving the complex circuits in the domain of G mains and advanced. It's given in NCRT. So we'll start with phasors. which I have already told. Z bar equals Z e to the power I theta. It's Z uh, cos theta I cap. Here we will denote it by I cap and J cap, right? So you can take it as X and Y axis. Z bar is here. This is theta. This is Z. This is the R cap direction. And R cap is given by this. You know R cap, right? This is from the polar vectors. It's cos theta I cap plus sin theta J cap. I think you know that. If you don't know, you can see the video of SM professor. You can watch the video of SM professor on how to apply the polar coordinates. How to apply polar coordinates is not necessary, I've already told you, but if you want to, he's a very good teacher, I've learned from him only. So the Z1 bar will be angle theta 1. This we are considering for the time being. The Z1 bar is the impedance, and we are denoting it by Z1 angle theta 1. It's just nothing but here the angles will be theta 1, right? We are physicists, so we're physics student, we don't like to write much. And Z2 will be Z2 mod theta 2. It's same as Zi e to the power I theta 1. It's Z2 I theta 2. Now notice one thing, if we multiply this, the angle will become theta 1 plus theta 2, which is Z1 Z2 e to the power I theta 1 plus theta 2. When we are multiplying things, the powers will be added, right? So this is the case here. Yeah. Same for if we divide. It will become Z1 by Z2 e to the power I, and write it theta 1 minus theta 2. You can same prove it like that only, right? I'm giving just a one shot type because I don't know how to teach much. So but then also I'm just trying. I know no one is saying, but then also so I bar equals I naught angle pi by 2. Listen, if voltage is given as the phase is, remember here it's V e to the power I theta or I omega t. We are taking omega t as a reference. So as taking omega t as a reference, the I naught value will be, I dash value will be I naught. It will lead by an angle of pi by 2. It will lead by a phase of pi by 2. Rather to say, it's always, it's nothing but here, see, it's if it's omega t, the I will be here. Or if in the complex plane it's omega t, it will make 90 degree with I, right? So this is the physical significance of this. And if you want to talk more, the complex impedance is given as V bar by I bar, which you will take at V naught by I naught angle minus pi by 2, right? 0 minus pi by 2, right? So now we will talk about purely resistive circuits. Yeah, let's talk about purely resistive circuits. Draw one resistor, draw one AC voltage, take the current, give the current, value arm plus minus, right? Instantaneously, at an instant we can write, listen my words, we are writing instantaneously because voltage is changing every time. So we cannot write here, we are not writing the RMS values, we are writing the instantaneous values, right? This is the situation. Here I will be equal to V naught by R sine omega t. So listen one thing, VR and IR will be always in same phase in case of resistive circuits, purely resistive circuits. In purely resistive circuits, I and V will be in same phase. Means if V is V naught theta 1, I will also be I naught theta 1, right? So this is the case here. And another thing to say that for reference direction, I have already told the reference direction will be like this. VR will be this side, IR will be this side, reference at omega t. You can take the reference any side, it will just rotate the vectors by that angle, right? Okay, so impedance is we got what, VR by IR. The phase is 0, means phase uh, leading phase, so it will be R0, right? For purely capacitive circuits now, purely capacitive circuits, what we will do, take a capacitor, introduce to your AC voltage, take I current, put a value Q plus Q minus Q, right? So here I am writing it. V will be equals to V naught angle 0. Q will be CV. We all know the charge at the steady state. CV naught sine omega t. CV 0. Sorry, CV 0 you can write. I dq upon dt. Apply the trick. What we knew? CV naught omega t. So CV naught omega cos omega t, right? I value will be IC, and it will be V naught by 1 by omega c. Listen here. Here when we are calculating, it's the charge, right? But in the case of here, just do nothing. In this I, take the 1 by omega c downwards. It will be give the same results, and it will be obviously cos omega t, or just take the 0. Listen one thing here, this we denote as a complex impedance. We don't get impedance by any physical methods. We get it by calculation. In the using of phasor calculations, we get the complex impedance. It's nothing else. It's V naught by xc. It's the denote for complex impedance. And here the current will be leading by an angle. So see here, it was sine omega t, but when we are doing current, it is cos omega t. Should be pi by 2, right? It is leading by an angle of pi by 2. As simple as that. Fairly good. Yeah. So in case of xc also, if we calculate xc, it's vc by ic. V naught angle 0, I naught angle pi by 2. So it will be xc minus pi by 2. So the impedance, the complex resistance, or the what we can say capacitive reactance of the purely capacitive circuit is lagging behind the voltage by a phase of pi by 2, and the current is leading voltage by angle of pi by 2. So remember this thing, VC and IC will have the same phase difference of pi by 2. IC will lead VC by angle of pi by 2. XC will lag VC by angle of pi by 2. Right. This is the content, and this is the theory which I can give. Uh, and remember one thing, lengths will be represented by the peak values or the RMS values. I have written the formula for RMS here. The RMS values, I think you have read it. Okay. So we will be doing about purely inductive circuits now. I think this is the last part. Maybe I'm not able to recall after that. I think one day I will take a session on leaky capacitors too. Let's try it purely inductive circuits. So draw an inductor and a voltage source. Take current I naught equals I naught sine omega t, L positive negative it is going like this. So magnetic field is like this, right? So it's coming out, so dot. But we will, the according to, you have learned Lenz's law, it will try to repose it, right? So it will try to repose it. So when we are angling towards the magnetic field by our thumb, the palm side will give the positive. So it will be like this, positive, negative, right? This, the current is going this side, it's going out, and if it's going out, give the angle, palm of thumb this side, or you can do it like this also. Yeah, okay, this is the thing. And I think this, it's very easy. And so don't talk much, I will do. The induced current will be, we know LDI by dt. Yeah, I've already told you. So it will be L I naught omega, apply the trick, cos omega t, or you can directly differentiate it. Cos omega t, omega will come outside, sin omega t it was, omega will come outside, because by chain rule, right? So here XL will be the inductive reactance, or the complex impedance, you can say. Here XL will be VL by IL, uh, I naught XL, angle is I naught's phase will be, it's pi by 2, IL is I naught 0. So thing to tell here, you can see cos omega t is changing from sin omega t, so phase difference will be obviously positive, and it will be of pi by 2, right? You can just write it VL equals I naught XL. So here omega L, this, writing clearly I naught omega L, this is the complex impedance XL here, right? And this is the thing. And in case of inductor, the voltage will lead current via phase of angle pi by 2. So I'm giving you one trick to remember this. Remember civil. For capacitor, the current, the for the capacitor, the current will lead voltage. For uh, inductor, L IV, the voltage will lead current by angle of pi by 2. This is the theory, and I think you can draw the voltage diagrams now. I'm then also drawing it. The voltage diagram will be like this. This side will be resistance R0, this side will be XL plus pi by 2 omega L, and its lags, so 1 by omega C, angle minus pi by 2. So this was the thing. And addition of complex number, I think you all know, it's very easy, like the vector product, z1 plus z2 equals a mod of z1 square plus z2 square plus z1 z2 cos theta 2 minus theta 1 root under z1 square plus z2 square plus z1 z2 cos theta 2 minus theta 1. This is the vector sum. And for the series RC circuit, I think the next day will be better. For now, I'm keeping it up to here. Next day we will, or I'm just teaching the method of phasors. Right, I think it not be a good bad part teaching it today, but no. Let's keep the series RC circuit for next day. We will start from here, right? So thank you for watching my video, and bye. Yeah.